Hello and welcome back to Statistics 1. We are in chapter 5. We are talking about discrete random variable, and now we are going to talk about the mean and the standard deviation of the discrete random variable. So we talked earlier about last time about the discrete random variable. We said that that's a variable whose values can be listed, and and we use the frequency distribution. We can come up with also the histogram. So we did all of those things, and today we're going to take a look at a few of these ideas. Now, we are associating probability now, so how likely is for one of the observations to occur. I can use the example from the book. I can go and pull the classroom as well. They are talking about age of 8 students. So we can relate to the example, and we can actually figure out the whole chart. So let's take a look at the data first. We have 19, 20, 20, 19, 21, 27, 20 and 21. So these are the ages of 8 students that are presented in this example. And now I can create the probability distribution off of this. So this could be one of the questions on the exam. Given data, create the probability distribution for X, where X is the age of the randomly selected student. So now if you are looking at this, you have the variable age, which is the X variable, and you see that the only ages in this particular example are 19, 20, 21, and 27. So there are 4 different ones. And this is why it's discrete, because we can list these 4 ages. Then I'm going to have the frequency. This is not given in a book in this way. I'm going to get the frequency because I want to be able to compute the probabilities. So the frequency, I have 2 who are 19, 2 who are 20, no, 3 who are 20, 2 that are 21, and 1 that is 27, for a total of 8. So that's my frequency. And now we are going to have the relative frequency, but that's actually, we can do the relative frequency, which is 2 out of 8, 3 out of 8, 2 out of 8, and 1 out of 8. So that's a relative frequency. But then the column that we actually are interested in is the probability column, which is the probability of X equals X, which is the probability for the discrete random variable. And that is going to be 0.225, 0.375, 0.25, and 0.125. When you add this, the probability adds to 1 because you will have to pick something. So now in a book, what they give you is only the first and the last column. So they give you the age and they give you probability. And the way we understand this and read this chart is it's very simple. What is the probability that you are going to pick a 20-year-old, right, randomly? Well, probability is 37.5%. So we can quickly see what is the likelihood, what is the probability that the student is either 20 or 19 or 27, so on. So again, we are focusing on the first and the second and the last column, and those are the only 2 that are given in the book. And now I would like to find the mean of all of this. Now we can find the mean, if you remember, this is our population. I can find the mean by simply adding all the ages, so sum of xi, and divide that by n. So summation of all these numbers would be, what do we have? 20 times 5, no, 20 times 6 is 120. And then Actually, these 19s and 20s, so yeah. So 8 times it's 160, it should be 167. Divided by 8 for the total of something. What would be the 20.875? Okay. So, 21 would be the average. Now, that's old. Let me label it as old. Old way to find the mean. You have the data, you add the data, and so on. But in some cases, you are not going to have data. You will just have probability as how likely is something to occur. In which case, you can use the method that we are going to learn as the new method to find the mean. And we will call that a mean of discrete random variable x, but it is going to have a different name. It's going to be called expected value. So here it is in red. Mean of a discrete random variable, also known as expected value, is going to be given by the formula mu equals summation of all x's times their probabilities. So we are going to add every x times its probability. So for our example up there, mu is equal to, and we have the variable variable x is 19 times the probability of 0 to 5 plus 20 times 0.375 plus 21 times 0.25 plus 27 times 0.125. So what I have done here is I simply multiplied every x. Remember, we are focusing on the first and the last column. So what I did is I went to the first column, picked up all my x's, which are the variables, and went to the last column and picked up their probabilities and multiplied them all together. So now let's take a look. What do we have? We have 19 times 0.25 plus 20 times 0.375 plus 21 times 0.25 plus 27 times 0.125. And no surprise there, 20.875. We already know that answer because we did the same average in a different way using the old method where we looked at the data. Now this new method is looking at the distribution of the discrete random variable, and this is just a new way to do it. However, the old way doesn't work when you have probabilities involved. The old way is just a simple average. This is what we call a weighted average. Just like your scores in a class. Your exam 1, 10%. Your exam 2, 15%. Right? Exam 3, 15%. Final exam, 30%. So each one of those has a different weight, and as you are figuring out your score, you have to multiply each individual score by the percent or how much it weighs. So I'm going to just briefly talk about it, because what we are actually doing now, these weights are probabilities, but it could be also percents for exams. So the same procedure, all right? The reason why I don't answer the questions of how I'm doing in class, I don't know. How are you doing in class? You have more information than me, because you can see your homework grades and other things that are done on the website. I have the least amount of information, and that is your exam grades, which you have as well. So what do you do? Let's take a look at weighted average, and then understand that instead of having these exam percents, you guys are going to have probabilities for your expected value. Same calculation. So let's say we have exam 1, exam 2, exam 3, final exam, homework, and the project. And that's that. So let's make up some percents. So first exam 10%, second exam 15%, third exam 15%, final exam 30%. So what do we have so far? That's 70. Let's put 20% on homework and 10% on project. Let's say this is the percent breakdown. So with this type of the percent breakdown, student keeps track of their grades. So let's take an example of a good student, okay? So the first exam grade 61, the second exam 73, the third exam 88, final exam 90, homework 100, and the project 95. Why is this a good student? You can see the grades are going constantly up. It doesn't matter where you start. It matters that the next one is larger, and the next one is larger, and the next one is larger. That is the characteristic of a good student. So now when you have this stuff, you are going to multiply these grades. 61 times 10%, that's 0.1. 73 times 0.15. 88 times 0.15. 90 times 0.3. 100 times 0.2. And 95 times 0.1. And then all of these things give you the values, and you add them all together. So that's the way you find the average in the class. So that's a 6.1 on the first one. Let's see the easy ones. This is okay, so that's 20, that's 27, the last one is 9.5, 73 times 0.15 is 1095, and 88 times 0.15 is 13.2. And now you add all of these for a total grade. So that's 17.05 plus 40.2 plus 29. Get 86.75. So that's 87 rounded, and it's a B plus. So this is the way you figure out the weighted average. You can also use it to figure out, when you can't make a decision about something in life, you can actually do the weighted average and see, right, if it scores a certain amount of points where, functionality, the design or whatever would play different role, right? You would assign different amount of points. So, if the design is more important than its functionality, which is common denominator for all Apple users. So there you go. So now let's take a look at some games of chance. And try to understand how the weighted average works. So, in the games of chance, right, you have all of these games that are played in casinos and so on. And all of those games are rigged for you to lose, obviously, which is the reason why casinos make so much money. Now, sure, individuals can win big bucks here and there, but over time, the collective body of people who play lose because the money these guys make have to come from somewhere. What is a fair game? Fair game is when you have a 50-50% right, chance of winning or losing. So if you have a coin, and that coin has heads and tails, and it's properly weighted coin, which means it's a fair coin, flipping that coin and getting heads or tails, so winning or losing is at 50%, and you have a fair game where the chance will 100% determine whether you win or lose. Now, let's go with flip a coin. And if you are flipping a coin, you only have in our variable x, you have heads and you have tails, and then associated probabilities are 1/2 and 1/2. So now, what is the expected value? Expected value, right? What is the expected value? I'm sorry? It's 50%, right? Expected value is going to be 50%, right? Because you are going to win half of the time and lose half of the time because it is fair. Now, what can I do in terms of the money for this? You see, I can come up with a different chart, right? I have heads and have tails. Let's say this is where you win. This is when you lose. Right, that's the variable. And see, if you win, you score $1, and when you lose $1. And so that's money. And the probability, obviously, of winning and losing is 1/2 because it's a fair coin. So what is the expected value? Expected value will be +1 times 1/2 plus -1 times 1/2, right? And you are going to get 0. Now, this is a fair game. It's a fair game because you can see that expected value is 0. That means if you play this game forever, no money in, no money out of your pocket. So that's the meaning of the whole thing. Now, what do we have as we play roulette, which is labeled as the fairest game at the casino? How many those little cells we have where the ball can land? 36 or 32? 34? Ah, great. I gotta look that up. And I'll be stuck with that knowledge that I don't need.
36.
36, I was right. Good. So, So roulette game has 30, well, let's do it this way. Roulette game has 18 red, 18 black, and 1 green. Now, when the roulette game is fair, you throw a ball, that ball bounces around, bounces around, bounces around. If there was no green field, this game would be fair, just like flipping a coin. So it wouldn't matter whether you play roulette or you play flipping a coin, because if the green cell doesn't exist, right, the green slot for the ball to fall in, then you would have 50-50 chance. But see that one green is just one extra little itty bitty piece for you to lose, right? Because the whole purpose is, if you bet red, right, your odds of winning are 18/37, and odds of losing are 19/37. Do we see that? So, let's say that the game goes this way. You have red, black, and green fields. You have red, black, and green fields. Let's say the money goes this way. If you, and this is where you win. Let's say red is where you win. And the other one, you lose. All right? So you win on a red, you gain $1, you lose on black, and you lose on green. And the associated probabilities are very simple to count, because you have 18 ways to win red. So that's 18 out of 37. You have 18 out of 37 to lose, and you also have 1/37 to lose on this one. So now what happens? If I look for expected value, which is mu, right, that's expected value. Now also, this is important to understand, guys. I'm using +1, -1, -1, that's dollars. And this is done from the perspective of a player, right? Because if I win, then the casino lost, right? So I have me winning +1 means that the casino lost with -1. So I can do this from either perspective. I'm doing this from the perspective of a player. So I win $1, so that's +1 times 18/37. Plus I lose $1 with 18/37. And another plus, I lose $1 with 1/37. And now you can calculate these odds. So to get the exact value, we have 18 over, it's 18/37 minus 19/37, which is -1/37. So that's what we are calculating, right? 1 divided by 37 is -0.027. Now this is money. So expected value is, I'll put for the player, is -0.027, but that's so technically every time they spin in a casino, they win 2.7 cents. Every time they spin it. Every time they spin it, on average, all of the players lose 2.7 cents. Now that's across all players. So someone is going to hit $10,000, but that doesn't matter, because for that one win of $10,000, so many others lost. Casino is open 24/7. So this is the average of all spins, all wins or losses, everyone ever playing since that system was built. And that's the expected value when everything is smoothed out. And when everything smooths out, everything is said and done. All the wins are paid, all the losses are paid, everything is pushed together. Casino makes the money. So every game is like that. There is no way of escaping, and you are not going to find a casino that has a flip a coin game or roulette game without a green field. Green field is the one that tips the odds in a casino, and you know what? Even if you are able to play 24/7 forever, that's going to be your loss because you have to lose because of the green field. So that's what the expected value is. We can use this to calculate many other things. This is used, and obviously not only for casinos. They would hire mathematicians to figure out the odds and all that stuff, and then they will have the game or not have the game. You can also use it to rig the games. I told you about adding a little bit of a metal, right? Flakes and so on a die makes it heavier on one side, which means that the number on the other side will come up more often. Again, you don't have to make something obvious that one side is clearly, right? But again, over time, everything happens over time. Over time, there's nothing. So when you skew something, over time it builds up a lot. In industry, expected value can be used, obviously, in medical field. You can figure out also expected value to wait for a phone call, right? For tech support or the ambulance, right? Getting to whatever it needs to get, right? Domino's is always going to beat it, obviously. It's the only country where you get pizza faster than the ambulance on a spot, and you still pay $8,000 for it. Yeah, that's actually statistically proven. And the odds are 100% that the cop will be there to give you a ticket, will not be there when you need it. Right? That's exactly, yeah, I know. So we can compute all of those expected values, and all of them are calculated simply by multiplying the variable that you have times, right? So let's take a look at, let's make up a game. Let's make up a game and see if we should play it. Remember what I said earlier? How about we cut the deck of cards, and so no, first you pick whatever card you want in your head. And what do you have? You had a 2 of clubs? 2 spades? All right. So 2 of spades. If you pick 2 of spades, you score A for the class. No more exams, no final, no homework, nothing. You can pack your stuff, go home, you're done. But if you miss, it's -10 on the next exam, and that's it. There's no other penalties for any other projects, homework, assignment, final, nothing. It's just the next exam is -10. Right? Yeah, you can do that. Let's see the expected value. Let's see the expected value of that one. Yeah, you take your chances, right? Terrible odds. Because your odds of winning are 1 in 52, your odds of losing are 51 of 52.
But the wins outweighs the losses. Like, I literally do not have to do anything for a semester compared to losing.
There's only a month left. It's not a semester.
I don't have to do the project, I don't have to do the next 3 exams, I don't have to do any homework. I'll take that off.
We'll have to play. You have your magic deck.
And you got that 10 points,
Yeah.
So it's really taking the...
We can spicy the odds, so if he misses, then everyone loses 10 points. Ooh, look at this one, right? Apparently you're on your own, man. Okay. So now we want to also take a look at the standard deviation. We'll do the draw right after the class, so you can have the witnesses as well. So standard deviation. Of a discrete random variable. It's a drv. Drv, yeah, drv. Discrete random variable. Drv. So we have the sigma is equal to the square root of summation of x minus mu squared times all of the probabilities. And or, you know, they like to have two different formulas for the same thing. For standard deviation, square root of summation of all x squared times the probability minus the mu squared. So that will be the standard deviation. Again, standard deviation measures the spread. So let's, in the book they have 7-line thing. I just want to go back to our age. Am I hearing a problem over there? I did not close the parenthesis. Where? I would say thank you if Rob was the one to tell me that, but no. You get nothing. So this is our old example for age. And the only two things that we need now, I'm going to put the data again because we have to expand on the chart, is the variable x and the probabilities that are assigned to the random variable. So we have 19, 20, 21, and 27. And the associated probability is 0.25, 0.375, 0.25, and 0.125. Great. So now we have this. We have also our formula for standard deviation. Formula set. That's delta. There we go. Formula says that we are supposed to do the summation of x minus mu squared times the probabilities. Well, we already know the mu for this one. We calculated it was 20.875. That was mu. So now what do I need to create those extra columns, right? That's the way we used to do standard deviation earlier. The first column would be x minus mu. That's the first column. And then we have to square x minus mu. And then we are going to multiply x minus mu squared with the probabilities. Then we are going to add those over here. And then finally take the square root of that number. So that's the roadmap. Not sure if I should use the word obvious. We use PEMDAS, right? Order of operations. You first do parentheses, then you have option between square or multiplication, well, parentheses, then exponents, so that's the next one. And now summation is applied to all of these, so you have to do the sum then, and then multiply with everything. And then you do square root at the end. So it's structured. So x minus mu. So we have what? Negative 1.875. It's x minus 20, right? 19 minus, right? Negative 0.875. 21 minus this is 0.125. And 27 minus 20 is 7.125. No, 6. And now we have to square each one of these numbers. So I have 1.875 squared. Keep 3 decimals at least, so 3.516. Now the next one is 0.875 squared, 0.766. Then the next one is 125 squared, which is 0.016. And 6.125 squared is 37.516. So this is when we square all of the x minus mu's. And then we need to multiply each one by their probability. So now we are multiplying these two columns. That's the end. So we have subtraction first because that's in parentheses, then we square, then we multiply, and the end we add. We come up with a total number over here when you add, and that number goes in the square root, and that's the standard deviation. So now what I'm doing is I am multiplying this with this, because that's the next step. I have 0.25 times 3.516 gets me 0.875. 879. 0.375 times 0.766.
Is that a 1 or a 6? So 3.5. Is that a 1 or a 6? I mean, a 1 or a 7. Oh. Is it 5, 6?
516. Sevens are crossed. That's the proper way to write it. I know you learn something every day. 287. You will never have those issues, right? Otherwise, I would never know how would you do if I gave you, like even if I gave you one of my passwords, you would not be able to figure it out, right? Because you would not write it a proper way. So it's like 1 lowercase l, okay, capital I 0. O, O, 0, lowercase l, 1, 1, and then capital I. There you go. It's a password. Good luck. Yeah, I know but if you write it the proper way, 1, lowercase l, capital I, right, 0, O, then it makes sense, right? What?
I used to write. I used to write my sevens like when I put the cost in 5th grade, and my teacher was like, "No, that's not how you write a sub." I got a coach there. I'll like,
That's why about 95% of people who teach should not. But yeah.
I see everybody doing lessons.
Yeah, or next semester I'm teaching one of those classes for teachers. So whoever is not crossing their 7s or Z's, it's gonna be bad. Like I have to deal with a 5 and an S. Okay, I have to deal with that, but I don't have to deal with 1s and 7s and number 1, number 7. There you go, 17. Done. All right. 0.25 times 0.016 is 0.004. Why are you doing that to me?
Because
I want to believe.
I you know what? I fat finger it sometimes.
What do you mean sometimes?
Sometimes I hit the wrong button. But I got it right this time. Yeah.
So now we're going to add this column, right? Because the next thing is to do the sum. And we take the square root of that. Two point 40. And that's the standard deviation. So for our example on ages, standard deviation is 2.42. From the mean. So you go this number, subtract 3 times, this number, add 3 times. It's the 27 obviously that is messing things up, right? Because these are consecutive. Without 27, what happens here? Right there, right? Good.
To the formulas. Okay.
You're welcome.
We did the first one, right?
Yeah. There's the second one as well. So there are a lot of cool problems. Let's take a look at the equipment breakdowns. 5.43. So, in a factory, right? The factory manager collects the data on the number of breakdowns. So this is the factory, and this is the equipment breakdown. So the manager is Why is this W? Equipment breakdown. Oh, there is a W in the breakdown. Okay, got it. So P of W equals W. There we go. So 0 breakdowns at 80%, 1 breakdown at 15%, and 2 breakdowns at 0.05%. You better get 1 when you add this, otherwise manager is not doing well. So this is the distribution, right? It's a discrete random variable, the amount of broken equipment per day. And you can use this to obtain the expected value, which is expected value. What do you expect? How many breakdowns do you expect per day? Right? So how many breakdowns do we expect per day? Well, you calculate the expected value. So what do we have? We have 0 times 80, so mu equals 0 times 80, 0 times 0.80, plus 1 times 0.15, plus 2 times 0.05. This is 0 plus 0.15 plus 0.1 equals to 0.25. So we are expecting about a quarter of a breakdown a day. The way you would read this is a breakdown every 4 days. That's technically the way you would read. So something will break in this machine, right? Or a tool or something will break every 4 days. You have to have something happen. That's the expected value. Can you go a whole week without anything breaking? Sure. This is a game of chance, guys. You can go a whole week without anything breaking. We are expecting a quarter breakdown a day, so times 4, we are expecting something to break. It's not guaranteed 100%, but we are expecting something to break every 4 days. How many breakdowns are we expecting in 200 days? Times 200, right? So, how many breakdowns in 200 days? I think they were not 200. I think they had actually a number. 250. How many breakdowns in 250 work days? It will be 0.25 times 250. And what do we get? 62.5. My number was better. What's a half a breakdown? Is the machine is limping or something? I don't know. Half a breakdown. And statistics, right? Round. So we're expecting about 63 breakdowns over a course of 200. You have to budget for these things. You have to budget for maintenance and parts. And all of these things are there, so for the production. You have to worry about it. It's a cost. It adds to the cost of production and making the product. That's that. So let's restart for the new, for the last section of chapter 5, and material for the next exam is over. Yes?
I just recopy the original.